Hello everyone. In this video, we'll be solving a numerical problem to find potential if electric field intensity vector and the initial and final positions of the charge is given. So let us start solving this numerical problem where electric field intensity vector is given and the coordinates of the point is given. We are asked to find potential difference, absolute potential, and with reference to the zero potential at some reference point is also given. Let us do one by one. I will first start with the first subdivision, then do the second and third subdivision so that we can easily understand one after the other. So for the first subdivision, the given electric field intensity vector I'm writing, which is 6x square ax cap plus 6y ay cap plus 4 az cap volt per meter. And the point coordinates m and n are given. M coordinates are 2, 6, minus 1 and n coordinates are minus 3, minus 3, 2. You are asked to find Vmn. So we need to write the formula for finding Vmn. Thereby we can start solving the numerical problem. Vmn can be given as minus integration E vector dot dl vector. The initial point or the reference is n and the final point, the reference is n and the final point is m. So you should know the convention. The second one indicates the reference, which will come as the initial position, and the first subscript indicates the final position that should come as the upper limit of the integral. So the reference is the initial position. Initial position is always the reference point, which should come as the lower limit, and the final position will come as the upper limit. So let us solve this numerical problem. So find E vector or dl vector. In rectangular system, we know dl vector is dx cap plus dy ay cap plus dz az cap. Now we should find what is this E vector or dl vector. I'll write E vector or dl vector over here, which is 6x square dx plus 6y dy plus 4 dz. Now we have to perform integration to get the potential difference. So Vmn will be minus integration of 6x square dx plus 6y dy plus 4 dz. And I should consider the three integrations, one for x, y, and z. For this, the limits for x, y, and z should be given correspondingly. The initial position is n and final position is m. So x will have the lower limit minus 3 to 2 and y will have the limits minus 3 to 6 and z will have the limits 2 to minus 1. We can perform the integration to get the answer. So Vmn is going to be minus 6x cubed by 3, limit minus 3 to 2, then here 6y squared by 2, limit minus 3 to 6, then 4 into z, 2 to minus 1. So I will be giving time for you to work out. You can pause the video, complete the integration limits application, and you can get the final answer. So the final answer for this is going to be minus 139 volts. Next, we can jump to the second subdivision, which is asking you to find Vm if V0 is at point Q. So let us talk about that. For the second subdivision, electric field intensity is same, which is 6x square ax cap plus 6y ay cap plus 4 az cap. And I will directly write E vector or dl vector, which is 6x square dx plus 6y dy plus 4 dz. You are asked to find absolute potential at M if V is equal to 0 at Q having the coordinates 4, -2, -35. Now, in this case, you are asked to find absolute potential. This is absolute potential, but reference potential is this. This is the reference. So, reference point should be taken at Q. So, first, we should find what is VMQ in this case. Because reference is at Q, which can be written as minus line integration E dot dl. Reference is at Q, and the final position is M. Now, we also know difference in potential VMQ can be written as VM minus VQ. So, this is the difference in potential, that is potential difference between M and Q. If Q is the reference, can be written as absolute potential VM minus VQ. These are already discussed in the theory videos of potential difference and absolute potential. You can refer those videos. So now, with reference to Q, you are asked to find VMQ, and from VMQ, you are asked to find VM. That is how we are going to solve this numerical problem. So from this, first, we should compute this VMQ, and second, we should compute VM. From this formula, we can write VM as VMQ plus VQ. But also one more thing is given, VQ is 0. So V at Q is 0 volts. That is what given in this question. So VQ is 0. Thereby, we will get VM is same as VMQ. Whatever we are finding VMQ, that is going to be the same over here, because V at Q is 0. So let us start doing this problem. So VMQ equals minus integration 6x square dx, where x limit should be given accordingly, and 6y dy, where y limit should be given accordingly, and 4 dz, where z limit should be given accordingly. We know the initial reference starts at Q. So Q coordinates should be the initial positions. So initial positions for x is 4, y is -2, z is -35. And the final position. So the final position corresponds to the point M. So for point M, the coordinates are 2, 6, -1. So you can check here 2, 6, -1. So I will write here 2, 6, -1. And now I leave this as your practice to complete this. I will write directly 6x cubed by 3, applying the limits 4 to 2, then 6y squared by 2, applying the limits -2 to 6, then 4z, applying the limits -35 to -1. This is going to give the answer, and I will directly write the answer. You can apply the limits and verify the answer yourselves. So VMQ is going to be -120 volts. And we also know VM is VMQ plus VQ. That also is going to be -120 volts, since VQ is 0. So the answer for absolute potential at M, if the reference is at Q, then the answer is -120 volts. Let us do the third subdivision so that you can have a better understanding of how to solve this similar numerical problem. So the third subdivision C says you're asked to find Vn if voltage is 2 volts at point P with the coordinates 1, 2, -4. Now this has to be taken as the reference. So this has to be taken as the reference, which is point P. V at point P is 2 volts. So we should find VNP first. First VNP should be found, and then we know VNP is Vn minus Vp. Thereby Vn can be found as, from this formula, we can find Vn as VNP plus Vp, where Vp is given as 2 volts as per the question. The formula for VNP is minus E vector dot dl vector. The initial position is P, reference is P, and the final position is F. We can write what is E dot dl. It is same as the previous two cases, which is 6x squared dx. the 6y dy plus 4 dz. Now we need to find v and p, which is minus integration 6x squared dx plus 6y dy plus 4 dz with the limits for x, y, and z corresponding to the initial position is at p and the final position is at n. So for p, the x, y, z values are 1, 2, and minus 4. And for point n, the x, y, z values are minus 3, and 2. So by applying these limits and performing the integration, you will be getting v and b. So in a similar way, you should do this. So 6x cubed by 3, limits 1 to minus 3. Then 6y squared by 2, limits 2 to minus 3. Then 4 to c, limits minus 4 to 2. I am leaving this for you to complete. You can pause the video, complete it, and then check the answer. So for this, you will be getting V and P as 17 volts. Now from this, we can substitute V and P as 17 volts, and you know Vp is 2 volts. So taking these two, you will be getting Vn as 17 plus 2, which is 19 volts. So this is the absolute potential at N asked in the question, taking point P as the reference, where the reference potential at point P is 2 volts, that is given in the question. I hope you have understood this problem. Thank you for watching the video. You can replay the video for better understanding.